In this video, we're going to look at how we can form triple bonds between and what the orbitals look like here in terms of how the atomic orbitals overlap. So our molecule we're going to look at for this, we're going to look at acetylene. We've been picking carbon-based molecules because we care a lot about the structure of carbon in organic molecules and things like that. Okay, so we know this forms a linear geometry based on Vesper theory because we just have the two bonds to worry about. But let's now think about how this can occur in terms of hybrid orbitals in valence bond theory. So what's going to happen here is that if we look at one of our carbon atoms, to get a linear bond like this, it mostly looks like a p orbital, but we need two separate parts. Remember, a p orbital is just sort of one thing. We need two separate p orbitals. And so we take one s orbital and one p orbital. So again, if we sort of sketch out our s and p orbitals, we're now just taking our s orbital and only one of the p orbitals and combining those to form, with two leftover p orbitals here, we're going to have two sp hybrid orbitals. And these form a linear geometry. So whenever we have a linear geometry in a molecule where there are just two electron pairs or two electron domains, that's going to be an sp hybrid situation. So we're going to have sp hybrid orbitals that form on each carbon atom, and this will form our, let me use a different color here, we're going to form our sigma bond right here in the middle, and then our hydrogens are going to be on the side over here, as we've seen many times, to form overlap between the 1s orbitals on the hydrogen and these sp hybrid orbitals on the carbons. So we're going to have three different sigma bonds. Again, these are single bonds that are forming. Now, what about the, again, we have two leftover p orbitals here. What's going to happen with these? All right, and so this is where we're going to start to form, right, our Lewis structure, we have a triple bond, so we need to start forming a triple bond. All right, so I'm going to move down here. So we have our sigma bond here between the carbons, another sigma bond here between the carbons and the hydrogens. Right, so these are our sigma bonds here, here, and here. And we're going to have two leftover p orbitals on each carbon. So one p orbital points up and down. Let me again use a different color here. And another one that points in and out of the page like this. Let me draw these ones in red. All right, so one p orbital here and a second p orbital here. And what's going to happen is we're going to get overlaps of these p orbitals in both this p orbital, that's the up and down p orbital, as well as the ones on the side. And this is where it gets really hard to draw. And I'm actually going to grab a figure from your textbook that shows this a little bit more clearly. Let me make sure I find the right one here. All right, this is the one I want. That is not the one I want. But same basic idea. I'm looking for the one that has not nitrogen, but acetylene. 9.28. There we go. This is the one I want. All right, let's make this a little bit bigger so we can read it. And we're good. Okay. So let's look at this. Let's look at this figure. So this is a figure showing what I was trying to show, but with a little bit better three-dimensional drawing. So again, here's our orbitals up here that are hybridizing. So again, only one of the s orbital and one of the p orbitals is hybridizing, and our unhybridized p orbitals are left behind. So these are the unhybridized p orbitals right here, and right here on this carbon, and right here on this carbon. And when these combine, we have, again, as I showed before, our sigma bonds that form here, here, and here. And then we have pi bond number 1 that's above and below the molecule. Again, that's only one bond, right? Just with pi orbitals, we get two lobes of it, just like we have two lobes of a p orbital. And our second one is in front and behind back here, and that's pi bond number 2. So we get two pi bonds that form at 90 degrees relative to each other. And this is how we form a triple bond. All right, so this is the basic idea is that we have different types of hybrid orbitals depending on the geometry. So just to summarize, And we can look at other molecules, other things besides carbon. We've just been using carbon a lot, but that's not the only possibility here. But to summarize, if we have a tetrahedral geometry, electron pair geometry, that's going to lead to sp3 hybrid orbitals. If we have a trigonal planar, that would be sp2 hybrid orbitals. And then that leftover p orbital can participate in another bond and form a pi bond. And if we have a linear structure, a linear geometry where we have two electron domains, that will be sp hybrid orbitals. And the direction that these orbitals will point will follow the geometry that we have. And again, these geometries are the same as what we get from VSEPR theory. And so this is a way to understand how do these atomic orbitals, these s and p orbitals that are not shaped like a tetrahedron or a trigonal planar structure or linear structure, the idea behind valence bond theory is how do we recognize, number one, how do bonds form? They form from overlaps of atomic orbitals. And number two, how can we get orbitals with the correct geometry? And we do it by combining the s and p orbitals to form these hybrid structures. Now, this can apply to expanded octet structures too, so we can look at this with octahedral geometries or with the trigonal bipyramidal geometries, but there the picture's a little bit less clear. There's a couple of ways to look at this. One, older theory is that you can use d orbitals to combine with s and p orbitals to make the correct geometries. And there's a slightly newer development of the theory that's in your textbook that we'll look at later if we have time. We may not get to it. But that's the basic idea behind valence bond theory. We'll go through more specific examples in class, looking at some other molecules. And see you then.